This past weekend, I had the opportunity to present my research poster at the Math for All Satellite Conference at Boston College on a topic that bridged the gap between two of my interests, finance and math. I looked into how the fast Fourier transform, one of the world's most powerful algorithms most frequently used in signal processing and image processing, can be applied to a concrete example in the world of finance in pricing options. While this research was not novel, I found that the intuition and motivation behind the concept was unclear and may be intimidating to practitioners unfamiliar with either of the two fields. That is why I wanted to bridge the gap and share how we can harness the amazing computing power of the FFT algorithm in solving a real-world problem. For those unfamiliar with options, I'll give a quick rundown. So what is a stock option? It's a contract that gives the buyer of the option the ability to buy or sell a stock at a specified price on or before some specified expiration date. We'll refer to that specified price as a strike price. And note that in the examples that I'll be giving, I'm going to be working with call options, which is the right to buy. The most important thing to know about options is how profit is made. If you don't know what a stock is, you can just think of it as a price that moves up and down like a random walk if you're more familiar with the math terms. So let the price of the underlying stock start at $100 and the strike price of the call option to be $110. So you have the option to buy the stock at $110 on the expiration date. Assume the price of the stock moves up to $120. Since the call option gives you the right to buy at a set price, you can now buy the stock at $110 and immediately sell it at the market price of $120, giving you a profit of $10. A couple things to note. The profit gained from having the option depends on the price of the underlying stock. Having that option to buy the stock does have value, so therefore the value of the option depends on the price of the stock and the probabilities of the stock price moving up and moving down. And also note, if the stock price does not go above the strike price, there's no reason to exercise the call because you don't want to buy the stock for more than what you can get it on the market. So now, we know how much profit you can make if the stock price goes up and goes down from the option, but what determines what price that you buy that option at? This is where the binomial option pricing model comes in. If you would like more information, you can find more online, because this is one of the most widely used options pricing model used today. Here are some underlying assumptions and givens about the model. I won't go into what some of them mean, but if you're curious, you can easily find more information online. So let's get into an easy base case example. Let the price of the underlying stock be $100 and the strike price of the call option to be $105. Assume that the price of the stock can move up by a factor U with probability P, or move down by a factor of D with a probability of 1 minus P. Now, as shown before, we know exactly how much profit can be made off of the call option depending on where the stock price ends. Now, if we assume the call option expires after the stock price changes one time, then we know exactly how much profit and therefore how much the call option will be valued at each state. Now, using that information, we can take the expected value and find the call option value today, before the stock price changes. Don't worry about the discount term, the e to the negative r delta t that comes before that. If you're unfamiliar with what that means, it's unimportant. Now that process of taking the expected value can exactly be seen as taking the dot product of two 2x1 matrices. Now just to recap, we used those ending call profit values and a little bit of algebra in order to find the previous term's call value. Now let's generalize that by looking at the call values after 3 periods. This can be seen as the stock price going through 3 days, or 3 weeks, or 3 months, or even 3 years. That is denoted by the 4x1 matrix with C1 prime, C2 prime, C3 prime, and C4 prime. These are the possible ending call values after the stock price fluctuates over 3 periods. Just like before, since we only know the possible ending call values, we take the expected value in order to find the previous period's call values. Taking each individual expected value can be seen as a sliding dot product of the probabilities matrix. Now, if you're familiar with convolution, you can see that this is exactly what we're doing. We're sliding one matrix, which is a probability matrix, over the ending call value matrix. And we keep repeatedly doing this to get the previous call values in order to go all the way back to the root of the tree, the current call value. If convolution is a new term to you, this is a very easy and intuitive way to think about the process. We're taking one matrix, sliding over the other in order to get a new matrix. On a very high level, we're taking two sets of values and getting a third set of values out of that. Now we get a little creative in how we can view convolution. We essentially take those two matrices and we wrap them around in order to get two circles, and we put one circle inside of the other. And just like how we were sliding one matrix over the other, we can essentially rotate the inner circle and take the dot products of the inner circle values with the outer circle values to get the same exact result as the two matrix sliding view of convolution. But instead, we are rotating circles. Now, this view of convolution as rotating around a circle is how we start to see the connection with the Fourier transform. Now, moving away from finance and into the world of math, looking at the Fourier transform, you'll often hear it as taking a set of evenly sampled points over time and decomposing it into a set of frequencies with their corresponding strengths. That's how it's usually used in signal processing. But today, we're going to use the DFT and look at it through a new lens as convolution. First, we start with the idea of roots of unity. If this is foreign to you, you can at least see how rotating around a circle can be connected to the idea of convolution. We're working in the complex plane now, so these roots of unity have properties that work well with moving around the unit circle. That's why we're using them. Multiplying roots of unity on the complex plane is equivalent to adding angles on the real plane. One little side note is that we define a reversal operation, so we go the other way around the unit circle. It's not too important in the big picture of the idea, so I won't go into the reason why we do it, but you'll see throughout in the notation that is denoted REV. In most textbooks, you'll usually see it in the first form, but in this case, it's easier to see it as a form of matrix multiplication and also as a set of polynomials looking at the coefficients. Now, stepping away a little from the numbers and symbols, we look at the discrete Fourier transform and its intuition and how it connects with the idea of convolution. Now, I'll make a little bit of a broad observation that convolution can be seen as multiplying two polynomials using their coefficients. However, this can be easily seen through multiplying two polynomials using the distributive property and comparing the result with taking the convolution of the two sets of coefficients. Taking a step back, we look at a different way of multiplying two polynomials. One fact is that an n-degree polynomial can be uniquely identified by sampling n+1 distinct points on that polynomial. So therefore, instead of multiplying out the coefficients of two polynomials, we can sample n points from each polynomial, multiply them pointwise, and uniquely identify the resulting polynomial from those sampled points. Now, going back to the discrete Fourier transform and this matrix representation, we can see that those roots of unity can be looked at as the coefficients of the sampled points. So if we can find a way of sampling points of two polynomials, pointwise multiplying those points, and using those points to identify a new function, we have a new way of looking at convolution. And that is a high-level way of seeing how we use the Fourier transform to sample points and then return the resulting polynomial, which is the same as taking the convolution of the two polynomials. One other side note that is actually extremely important to the motivation behind this whole concept: the fast Fourier transform. The FFT algorithm is simply a faster way of computing the discrete Fourier transform. It does this by factoring out the DFT matrix into simpler matrices that are computationally less expensive, taking the computation time of the DFT, which is O n squared, to O n log n. In application, the FFT is synonymous with the DFT because they achieve the same exact result, but the FFT is way faster. Speaking in less technical terms, going from O(n) squared to O(n) log n time means that as we perform the operation more and more times, proportionally, the algorithm becomes more and more efficient. I put a little derivation of the FFT algorithm here, but I encourage you to look more into it because it takes an already super useful algorithm and makes it that much more applicable and useful in the real world. So zooming out a little, we now have a new way of viewing stock option pricing as convolution, and we also have a faster way of computing convolution. And the result is this: a beautifully simple equation that gets a closed form solution to the starting call value. In addition to how simple it is, the solution also can be computed way faster than the normal way of just using convolution. But you may be wondering, what is the motivation behind all this? Why do we even need a faster way of computing call option values? On the market, millions of options are being traded every day, and the stock prices change every second. So tiny price changes happening at high speeds can be the difference between losing and gaining millions of dollars. So efficiency and speed, in addition to accuracy, are extremely important. As an extreme example, some institutional traders invest in the most advanced technology and model research in order to make profit by simply being faster than everyone else. So in conclusion, we now have a way to turn the binomial options pricing model calculation speed, O(n) squared, to O(n) log n. I thought this was pretty cool because it brought two seemingly distant concepts together by viewing both of them in a new light. Some further topics that I plan on looking into are using the continuous time option pricing model involving stochastic calculus and the continuous Fourier transform, and also using the Fourier transform and convolution for image processing. Thank you, Professor Matthias Hassler, and also the Boston College Math Department for making this possible, and thank you for watching.